Okay, hello everybody. So let's try to discuss about some highlights of the French RISC-V research opportunity workshop we had 2 weeks ago exactly today. Okay, so just to start on this as a broad view on what we're going to talk about, you know that NCA Patterson got the Turing Award for their work on RISC architectures. And they make quite a strong statement during the lecture. It's a new golden age for computer architecture, domain, hardware, software, co-design, and open instruction set. So that's a bold statement for the future which is ahead of us, and which is very interesting. So just a small overview, what is RISC-V? So if you look on the front page of the foundation, you will see it's an open free instruction set architecture. They say it paves the way for the next 50 years of computing design and innovation. There are several things into that. There is several specifications which are out yet at the moment. There is user level ISA, compressed specification, privileged instruction set. Also lots of software tools to compilers or to generate architecture or and designs. And several stuff like that. RISC-V is also a foundation, which is incorporated in Delaware in the US. As this kind of organization, it has members, working groups, it issues specifications. At the moment, there are the base one for 32, 64, and even 128 bits instruction set. And if you look carefully, it doesn't just describe instruction set, but also SOC templates. Which is very important because for those who remember, it was very painful to get Linux to work properly on various ARM SOCs because the SOCs were so much different one from another. It took several years to get to a point where the Linux was really cross-usable. They own the RISC-V trademarks, they have a directory of tools and all that, and they organize regular events. So I had the chance to go to the Barcelona event in last May, and this is where I personally discovered this. I know about RISC-V, but knew until then that it was very active. The next summit is in December in Santa Clara. So just to give an idea about the member of the RISC-V Foundation, so there are the usual suspects. There are people which are not on the picture, like Microsoft, Amazon, Apple. Facebook is less clear because it seems to be a sponsor of the next event. There are also people which we would think we should be there, like TSMC or big integrators like Bosch, even research center in Europe. There are other people which, although are already there, like Force Institute here, Low Risk, which is working on a low-end RISC-V processor. And just something which I discovered down there is Western Digital, for instance. They bet the farm on RISC-V. They ship over 1 billion processors per year in the hard disk and SSD. And they decided to make the transition completely over several years to RISC-V. So that's a bold statement. And Andes Technology, which is a Taiwanese company I didn't even know about, which had their own architecture with their own instruction set. They ported the Linux kernel on top of it. They had a couple of extensions and stuff like that. And they decided to move away from their own architecture and to move everything to RISC-V, except the extension on DSP on general purpose register, which we moved back to RISC-V. So that seems to be quite a momentum beside that. So talking about the research opportunities, the feedback loop from hardware to software is obvious in research. We get new hardware and we try to use it as software people and to run on software on top of that. What RISC-V brings is it's a practical way to make the feedback in the other loop. We can now have initiative where people can, from software, derive request for on the hardware or implement them, work with people with hardware to propose new ideas. Also, the application which used to target separately hardware and software can now propose improvement on the full stack, including hardware and software. So the reason for those opportunities is that the ISA is public in the sense that you can implement it without any trouble. There is open source design IPs, so you can start with that. And there is also something which might not be directly related to that, but which is nevertheless significant, is that there is a slowing of the end of Moore laws. So the future seems to be about heterogeneous architecture and accelerators, so we need to be able to go deeply into the architecture to attach them. And if the Moore law slows, then the little guy can catch up. So we thought it was interesting to kickstart this kind of collaboration, to see what kind of collaboration can be done by RISC-V. And so we tried to organize a workshop for the French ecosystem. So it was, let's say, 2 weeks ago. We had like 80 people. It was only academics, an invitation only. We tried to keep the format very short presentation, not so much about the achievement, about the team, but more about, okay, what they are fluent into, what is their domain of expertise, and especially what do they see in terms of new opportunities, new collaboration they would like to have, or new things that they will have to do, because RISC-V will change the landscape anyway. So we had a couple of presentations and then some question and answer with all the speakers. So this is the schedule we had on the morning. It was a full day meeting. Just a small highlight on two presentations, which were, by the way, colleagues from CA, but they are guys working on hardware. The first one is about a kind of big little implementation based on RISC-V architectures, where they can work on task scheduling and work down into the platform to put their software on top of that. The other one is Eric Guttmüller's team. They are working on a scalable cache-coherent mini-core architecture. So they used to use MIPS processor, which are very old, not so much software to work on it. So they could use it on their own to assess their development and make sure stuff works properly on the chip they make. They are making the transition to RISC-V, and this will be a nice vehicle to provide to other people in the operating system research community, for instance, to deal with those and to work at the operating system level. Because at the moment, the only thing they can do is work at their own level, which is hardware. So in the afternoon, we had other session. I will go into some more detail about those sessions. Some of them. Okay, so one of the first presentations which was interesting was from a colleague working on ultra-low power software-defined radio for IoT protocols. So there is lots of variability in protocols, so you want to put some stuff in software to not redesign everything when you move from Sigfox to LoRa or to Bluetooth Low Energy. And we can see that this is a requirement at the end of the experiment. So it's a mix of low power issues and arithmetic issue related to signal processing and treatment. So these are really, if an architecture can address both of them, then they can move to their software-defined radio and achieve their objectives. So it seems to work, and they move ahead with Codazip. I think it's a startup from Czechia. Which have got their own implementation of RISC-V. So this is really a deep application in the radio field. In more generally, Florent Dinechin from INRIA is working on computer arithmetics. So his question is to he makes several, he generates operators for in the HDL. So the question is why should you have a divider or a square root in processor or elementary function, depending on application of the field you try to target. And he said the opportunity for him is that dark silicon make it so that you can't use 100% of the processor 100% of the time. You're going to burn the chip. So you can use the area at energy saving to implement rarely used function. Make it very efficient, so you decrease the power consumption, and when you don't use them, they are basically thermal propagators for the rest of the processor. And the interesting thing in this field is that the trade-off how to implement operators or to implement them or not varies quite a lot with time. For instance, in a divider, it used to be the case 25 years ago that yes, you need to put it in hardware. The Merced people, Italian people decided in early 2000 that no, that's useless. Better put another multiplier and add, which can be used for division, but can be used for other thing again. 2018, the consensus seems to be that the ARM people, for instance, are making exactly on this dark silicon requirement, are putting back the divider into the chip. And the same goes for elementary functions. Sometimes it's yes, sometimes no. It seems that every 10 years it changes. So the fact that you can have an architecture and experiment with various operators is also a very strong improvement for this kind of research. In operating system, we had Vivien Kema, which presented issues with that, or opportunities, should I say. There is, I'd say, a growing gap between architecture and OS research. The two communities haven't discussed together, which they should. And but RISC-V provides a great opportunity for them. So, for instance, it would allow to revisit the usual OS topics, memory management, what the memory hierarchy should be done, what should be the hardware feature, which one are exploitable by software, which one are not, scheduling, synchronization, that kind of things. But also there is intriguing research direction for cloud server, for instance, better support for performance monitoring. So that relates to the previous discussion, how to really assess the performance of all architecture, of workload which execute. Support for very short tasks. It seems in the cloud now we've got very short tasks which are microsecond scale. So how do you monitor that? How do you even provide protection domain for those and that kind of stuff? Performance and security isolation mechanism, and even to think at the scale, at the rack scale, what stuff should be in the architecture for that. So that's for the operating system field. For high performance, we had a presentation by William Jalby from University of Versailles-Saint-Quentin. His main research topic is, okay, I've got the huge pile of HPC code, where do I start to optimize it? So one of his points is that the hardware performance counter, which you'll be tempted to use for that, are really unusable, basically. They change from platform to platform, they are undocumented, they don't necessarily behave as they should. So these counters were made to debug the hardware, not so much to help the software guys. So the next question is, what software guys do want in terms of instrumentation of an architecture to make those analyses, like the previous presentation again. How to put that into the architecture, and it shouldn't be too costly in terms of performance, etc. But that's a whole area in which now people can suggest ideas, whereas it used to be proprietary information of Intel and ARM before that. There are a couple of other topics which I won't go into much detail, but for instance, in safety, avionics, and so you want auditable development process, not only the software, which is already very much audited, but you would like to have that also in the hardware, and even in the hardware, the open source of the SOC is the first step, but after you've got all the design steps to go to the tape out and to the circuit, you want some credibility of the architecture, so there were a couple of presentations on that. That will allow to make, the openness of the architecture will allow to make research on that much more easily. Same goes for security. You want some sort of auditable development channel. We've heard about lots of vulnerability based on side channels like Spectre and Meltdown. Compilation, when you make compilation, there is whole sort of information that you have into the compiler, which can be provided to the architecture at runtime, like access patterns in the memory, which can be propagated into all the way to the memory controller, maybe. Also, if you've got that amount of cache, maybe it would be nice if the compiler could segregate into half the cache and half in a scratch pad, which could be used for some computing kernel. So there is lots of opportunity which can belong to that also, to that field as well. Then more generally, they specified 128-bit architecture, but what an OS will look like for those kind of architecture, which is make a huge addressing space. We can imagine to have a full HPC machine in a single address space. And what is the impact? For instance, there is NVRAM coming along. That will necessarily have some impact on the operating system, on the compiler, and that kind of thing. So the fact that we've got an architecture which is open will allow for broad experiments on that. So just to summarize, this picture is taken for the presentation by Nicolas on 2 weeks ago. This is for safety critical industry, aerospace basically, but really it summarized pretty well the benefits of using open architecture like that. You've got the simplicity of the architecture that you can use. There is the open source, the modularity, you can plug your own stuff into it. There is something which shouldn't be underestimated, is that it will take time to propagate to the industry. So the speed of research industry is different. Another kind of issue is that it might not go as quickly as we think it will. It's difficult to predict how quickly it goes. One real difficulty is that hardware-software development cycles are very different. From an ID to an ASIC, and that you test, etc., it's several years. If you've got an ID in software, it can take much less time to implement into your system. So there is really an issue in the community. How do we synchronize hardware and research schedule? And especially we will need iteration, so new hardware, new software experiment, and new hardware again, so how to iterate on that. Obviously, the current architecture won't go away, so the impact of RISC-V is difficult to assess, but I think it should be huge, but we don't know exactly where it will start for. The impact of Moore's law slowdown is actually helping, because this allows the little guys to catch up instead of having Intel being the front runner with two node technology nodes in advance. So that will slow down the pace of innovation, will help to benefit for the design. So it's not so easy. There will be issues. Then as a software guy, I like very much this quote by Alan Case. So if you are serious about your software, you should make your own hardware. Okay, so as conclusion, it's opened a wide range of opportunities, RISC-V, for hardware software co-design. It bring together the people which it can bring together people which are to work separately, because the processor was something which was not negotiable. It was provided by commercial companies, so we need to get to know each other. And one thing that we note also doing that is that there are few, for obvious budget reason, fewer teams in hardware design than in software. So that might be a bottleneck at some point. We plan to have other rencontres such as that. We plan to make one early next year. This time to open it to industrial partners. It will probably be in Paris and not in Grenoble. And that's about it. So the presentation of the workshop will be online, and we plan to do that in the coming weeks. There will be online in the public website. At the moment, only the program is available. And that's about it.